Welcome. In this screencast, we take a look as a Calculus 2 class at the very beginnings of infinite series. Now, series are things that in theory we learned in high school. So let's take a look at what we mean in Calculus 2. An infinite series is an expression of the form. And then you have this capital sigma, and there's this n equals 1 down here and this infinity up here, and we're adding up the a sub n's, and that's a1 plus a2 plus a3 plus dot, 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 period. So we write a plus and 3 dots, and then this period ends the sentence. For each positive integer k, the sum of the first k terms, that's the sum of the first k terms, that's the sum of the first k terms, is called the kth partial sum. So here's the big idea, and I'll keep this on the screen. If the sequence of partial sums converges to a real S, a real number S, then the infinite series converges to S. So if we're trying to figure out if this series has a sum, it's infinite, but does it have a sum? We look at the partial sums and we figure out what's happening to the sequence of the sum of the first two, the sum of the first three, the sum of the first four, the sum of the first five, and we look at that sequence of partial sums. And if that sequence of partial sums converges, then the series converges. The most popular kind of series, the one we'll come back to over and over again, is the geometric series. The geometric series is the sum of some number times some ratio to the n minus 1. And here's what we know. If the absolute value of r is less than 1, then the sum of the geometric series is first term over 1 minus r. If the absolute value of r is not less than 1, then the sum of the geometric series diverges. So these are things that we know, they're in our toolbox, we take care of them, we keep them around. So geometric series. Consider the following. 1 plus a half plus a fourth plus an eighth, and so on. Does it have a sum? 3 minus 3/4 plus 3/16 minus 3/64 plus, and so on. Does it have a sum? Well, you should know. You just talked about it on the previous slide. What's the common ratio every time? Multiply by a half, multiply by a half, multiply by a half. And since we're multiplying by a number whose absolute value is less than 1, then the sum of this series is first term over 1 minus r. And that happens to be the number 2. Similarly, how do you get from 3 to negative 3/4, or negative 3/4 to positive 3/16, and so on? You multiply by negative 1/4 every time. And since negative 1/4 has an absolute value less than 1, this sum is first term over 1 minus r, and that happens to be 12/5. Well, what about the sum as n goes from 1 to infinity of 3 plus 4 to the n over 5 to the n? How do we break that up? Well, we break it up into the sum of 3 over 5 to the n and the sum of 4 to the n over 5 to the n. And we can do that because that's a plus sign. So we're adding addings. Adding additions, that's probably better. So what are these? Let's deal with them individually. We sub in n equals 1, n equals 2, n equals 3, and so on. This is 3/5, 3/25, 3 1/25, and so on. This is 4/5, 16 25ths, 64 1/25, and so on. Both of these are geometric series. In this one, the r is 1/5, so we would do first term over 1 minus r. And in this series, the r is 4/5, so we would do first term over 1 minus r. Make sure that you're okay with this r being different than that r. Make sure you're all right with that. This fraction is equal to 3/4. This number is equal to 4. And so altogether, that's 19/4. Boy, does this bring back everything we love about fractions. Hey, speaking of fractions, let's express 0.353535 and so on as a fraction. 353535. Wait a minute. What's that? 353535 and so on. Well, let's look at it in chunks. This 35 is 35/100ths. This 35 is 35/10,000ths, right? Tens, hundreds, thousands, 10,000ths, right? This 35 is 35 over a million. Tens, hundreds, thousands, 10,000s, 100,000s, millions, millions, and so on. Well, what's this? This is a geometric series where the r is 1 over 100. So the sum is first term over 1 minus r. And that happens to simplify to 35 over 99. And you can confirm on any calculator that 35 over 99 is this repeating decimal. But geometric series are not the only kind of series that we study. Let's take a look at another kind. And we'll do it by way of example. Let's find the sum as n goes from 1 to infinity of 1 over n times n plus 2. 1 over n times n plus 2. Well, what in the world is that? So if you write out the first few terms, it's horribly unhelpful. Like there's a pattern with the denominators, but this is nothing discernible. I don't know. It's not arithmetic. It's not geometric. It's not helpful at all. So what do we do with that? Well, we rewrite this. We rewrite this using partial fraction decomposition. And if we do all the work with partial fraction decomposition, this is 1/2 over n minus 1/2 over n plus 2. Why do I care about that? Well, let's just factor out the 1/2 because we don't really need it. And then let's substitute different values of n. If you substitute n equals 1, this is 1 minus 1/3. And then if you substitute n equals 2, this is 1/2 minus 1/4. And then if you substitute 3, this is 1/3 minus 1/5. And if you substitute 4, this is 1/4 minus 1/6. And this goes on for a while. But watch what happens. The 1/3 and the negative 1/3, the 1/4 and the negative 1/4. The negative 1/5 is going to cancel out with the 1/5 here. The negative 1/6 is going to cancel out with the 1/6, and so on. And so what's left? Well, 1 plus 1/2. And we've got an answer. Why is it called a telescoping sum? It's called a telescoping sum because it collapses, like the old style telescopes used to do. It collapses. Kind of like you did after I put you through 11 plus minutes of calculus video. Well, thanks for sticking around this long.